Welcome to lecture 2.1b. In this lecture, we'll talk about some algebraic tricks for harder limits. If you've been following along in your textbook, you'll realize that by now we've been through the first half of this section, including limit properties and piecewise functions. And this video, I'm going to be doing examples 5 and 6 and 9. And it's worth having your textbook out, so take a moment to grab that if you don't already have it out. Let's get started. So far, we know a total of 4 strategies for finding the limit. We know that you can use your graphing calculator to plug in values that are close to x, and then we can estimate what the y value will be. We also know how to look at the graph, whether it's a graph on paper or in your calculator, where we find the spot where x equals a, and we look at what's happening as we get closer to that point. And we saw an extra strategy, which was how to use the 2 different sides, the one-sided limits, to really be precise about the limit. And then in last night's video, you saw that for polynomial and rational functions, the easiest thing is just to plug in the number, which you can do as long as it doesn't equal 0 on the bottom. Now, out of these 4 strategies, the right-hand 2 are a little bit different than the first 2, and I've indicated that by bolding in blue. Why do you think I consider these right-hand 2 to be different? Right, so you probably identified that the right-hand 2 strategies are the strategies that I would consider to be proof, and not just me, actually, any mathematician. These strategies of plugging in or of using the definition of a one-sided limit are really firm places. You can be confident in your answers. Doesn't mean we don't use these other strategies, it just means that for some limits, these strategies aren't going to be enough. And so the next question, the question that drives today's video is, what if these 4 strategies aren't helping? For example, take a look at the 4 limits that I've listed down here at the bottom. These limits all have something in common. See if you can figure out what it is. Okay, so you probably just identified that these are all examples of limits where we can't plug in because we would get an undefined value, a 0 on the bottom, and where we also don't really have an idea about what the limit's going to be. So it turns out there are 3 possibilities if you have a situation where your algebraic methods of plugging in don't work. The 3 possibilities are either the limit exists and there's an algebraic way to prove it, it's just one that we don't know yet, or the limit doesn't exist and we can use one of the strategies that we know to explain why. Or, and this is the gray area, there's a chance, and you should be worried about this, there's a chance that the limit can't be determined, that it isn't just a problem of us not knowing enough. And it isn't that the limit doesn't exist, it's that nobody knows. And in fact, this kind of complicated gray area is one of the reasons that mathematicians are still researching, right? Math is not complete yet. This is the exact kind of question that somebody who studies math at the PhD level might be studying. They might be taking a really strange limit and trying to figure out a new way, inventing a strategy to determine what it is. Luckily, that's many years in your future. For today, we're going to be using some algebraic methods that are tried and true. Before we go to the algebra, I wonder if we can just get an instinct for what we expect to happen using a graph. So grab your graphing calculator and one by one, plug each of these functions in and look at the graph near this green x value for each one and see if you can predict which one of these you think will have limits and which one, if any, won't have a limit. When you press play again, I'll show you what I got. Cool, so you've made your predictions. Here's what I would have done. You may be using graphing calculator, but I'm going to use Desmos because it's available to me. And when I plug in this first function, tan of x over x, it looks pretty funky. We can take a closer look here. And I know that out of all this mess, I really just care about what's happening as I zoom in here close to where x equals 0. And what I see is that it looks like the function's probably around 1 because it's halfway between 0 and 2. In fact, I can zoom in closer and closer. And one of the things I notice is this looks like a pretty normal function. I don't know what all the fuss is about. And the trace button is going to allow me to get an even closer sense. So here I am coming from the right-hand side, tracing this graph. You can watch the x and the y values change as I get closer and closer and closer and closer to 0. And I get almost there, and then whoop, there is this one moment where something crazy happens, which is right at that point, which you don't see unless you're looking really closely. Actually, at 0, this function's undefined. And that should make sense to you because at 0, you can't plug in a 0 on the bottom of a fraction. But what I also see is that it really looks like the y values near 0 are all approximately 1. So my guess is that this limit equals 1. And the question in my mind is, well, how can I prove it? Similarly for the second one, here's what the second graph would look like. So I've got my function here, and this function looks like it's a really kind of narrow one. It's got that curved square root shape, which makes sense to me. And again, I'm zooming in to get closer and closer to 0 here, and it looks like a pretty normal function. I can do the same tracing thing, but even without going through all of this, I'm going to guess that this function has a limit, and it looks like the limit is somewhere around 0.25 maybe, something like that. That would be my guess. For the next one down, here's what this is going to look like. I'm just going to speed through these a little bit. Ooh, this is a great function. As I zoom in, again, I'm interested at 0. This one looks a little bit more interesting. In fact, I'm zooming and zooming and zooming. I'm really close to the graph now. And I don't have very much clarity. I get really close here. I'm going to guess that the limit's probably around 0, but I don't feel as certain about this one because it looks like it's wiggling and it just really seems unclear, even zoomed in so far. The last function looks like this. Of course, I'm going to have to zoom my graph back out. And the last function's limit we were interested in was at positive 2. So there's the graph. Here's positive 2. And for this one, instead of zooming in, it looks like I have to zoom out because it's really hard for me to find where the graph is going to cross. And for this one, I'm zooming out farther and farther and farther, and I'm struggling to see what's happening. In fact, the graph jumps up here, which means the last one, I don't think there's a limit. I'm not seeing it. Now, this is all just a hunch. We're just looking at graphs. It would be nice if we could do more than just give a hunch, and that's the purpose of this video. I'm going to show you now 3 simple tricks that you can try if you ever come across a limit that you're struggling to understand, particularly a limit where you can't just plug in values. Here's the first trick. The first trick is to use the product rule in a sneaky way. Remember, the product rule means if you can rewrite the inside of your limit as a product of 2 things that you understand, then you can find the limit easily. In order to solve this limit, we're going to need to know this fact. And this is not something that we've been over before, but it's a fact. You can take it as sure, and I'll motivate it a little better in class. But the fact is that the limit as x approaches 0 of sine of x over x equals 1. As I go through this example, I'm going to reference a couple other trigonometry facts. As you take your notes, I expect that you circle or star anything that I use that you don't recognize, and you ask me about it, because the purpose of these videos is that you learn to recognize what's going on, and it's your responsibility to recognize if you're missing foundational skills in this case. So the approach for this is I'm just going to try things that I know. I don't immediately see the right way to take this limit. So one thing that I know is that tangent is the same thing as sine over cosine. And so instead of tangent, I'm going to rewrite it as sine over cosine. And of course, I'm still taking the limit as x approaches 0. So make sure you copy down the whole function. And you'll notice what I've done is I've really just rewritten this function. Now, I still don't really know what the goal is. I'm just kind of playing around. But I do know that this notation, this is kind of like 2 fractions or nested fractions from Algebra 2. It's the same thing as saying the limit as x approaches 0 of sine of x times 1 over cosine of x. And the x is still on the bottom. I'm just rearranging things here. Well, this whole thing I can rewrite as the limit as x approaches 0 of sine of x over x times 1 over the cosine of x. All of this is just me playing around with the symbols. You won't necessarily know if you're doing it right. You're trying something, and if it helps you, then yeah, that was the right thing to do. In this case, all of my playing around with the symbols has actually helped me more than you may realize. Think about the problem that we started with. The problem was I can't plug in 0 because I would get an undefined value. Well, I've actually solved that problem because although I can't plug in 0 right here, I do know that the limit of these two things multiplied together is the same thing as the limit as x approaches 0 of sine of x over x times the limit of the second part. This is the product rule. This is the more important application. We did the easy examples before. I can split this limit because of multiplication. Now the reason this is helpful is I don't need to substitute 0 into this limit to solve it. This is a limit that we know the answer of. This whole thing equals 1. And I can plug 0 into cosine. Cosine of 0 is 1, and 1 over 1 is 1, so this second limit, I can use substitution, and I get a 1, which means I've just solved my limit. The answer is 1, and if you remember, that's actually the same answer that we predicted based on the graph. Following my work, see if you can think about a way to do the second one, the one that says for you. Great, let's see how you did. So the first thing I would have done to solve this would be to recognize that when we say the limit of sine squared, what we really mean is that we are taking sine and squaring it, and that was a point of confusion in the last test. So really, it's saying the limit as x approaches 0 of sine of x times sine of x over x. And once I've got it in that format, I realize I can use that same little trick where I split out sine x over x, and then I can use the product rule, which I do right here. And this allows me to say, well, this first limit is a limit that I know. The answer to that is 1, and I've just memorized that. And the second limit is a limit where I can plug in, because plugging 0 in for sine of x just gives me a 0, which makes the solution to this limit 0. The second trick that I'm going to show you for limits has to do with something called conjugates. And in this trick, we're actually going to engage another fact that you should know from pre-cal, and that's the definition of a conjugate, which I have right here on the screen. Conjugates are useful because when you multiply something by its conjugate, the difference of square engages, which sometimes leads you to kind of surprising results. So notice for this example, first of all, I can't plug in 0 because I'm going to get a 0 on the bottom. Furthermore, there's nothing to rearrange here sneakily. There's no multiplication going on. So what I'm going to do is I'm going to multiply the top and the bottom by the conjugate of this expression. And this is not a technique that's always going to work, but it's something that is sometimes worth trying. So in this binomial, just recognize that the first term is this whole thing. So the conjugate is going to keep that whole first term the same, the x plus 4 square rooted, and then it's going to change the sign, so this will be plus 2 instead of minus 2. And I'm going to multiply that on both the top and the bottom, which I'm allowed to do by basic algebra rules. On the top, what's going to happen is it's going to FOIL. And the a and the b, a times a times b times a, b times b, are going to have a difference of square pattern, so that the answer is going to end up being a squared minus b squared down here on my next step. So as I bring my limit down, I've got the limit as x approaches 0 of the square root of x plus 4 squared minus 2 squared over x times the square root of x plus 4 plus 2. And I could distribute that out, but I'm going to wait and do that a little bit later if I can. From here, we can simplify the top. And I'm actually about to run out of time, so I'm going to end this video here and finish this example on the second one. So pause where you are and continue on to the next video. I'll pick up right where we left off.